So now let's put all of our knowledge about drawing Lewis dot structures and judging different resonance forms into practice. I would like to practice by drawing two resonance structures for the polyanion bromate, BrO3 minus. I would like you to draw one resonance structure that obeys the octet rule for bromine. Bromine is the central atom here, being the unique atom. And one resonance structure that gives a formal charge of 0 on bromine. And then judge which would be the preferred or more important resonance structure of the two. So we can start off by using the handy hints. BrO3 minus, I have bromine, I have 3 oxygens, and I have a negative charge. So if I look at the periodic table, the available electrons for bromine are 7 valence electrons. For oxygen, it would be 6, but there are 3 of them, so that's 3 oxygens in the anion, so that's 18. And the minus charge counts for 1 electron. 7 plus 18 plus 1 is 26 electrons that are available. Now, bromine and 3 oxygens, each of them would require an octet, so that would mean that I have 8 times 4 is 32 electrons required for all 4 of those atoms to have the octet rule satisfied. So I'm going to figure out that I need to have 32 minus 26, 6 electrons shared. Dividing that number by 2 gives me 3 bonds. All right, so now I can start to construct my molecule. I have bromine with 3 bonds to those 3 oxygens, so I'm drawing them all around it. Now I need to start thinking about lone pairs. I have 26 electrons available. I used 6 of them in bonds. So that means that I have 20 electrons in lone pairs. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now, I ran out of space for the oxygen, so 19, 20 I have to put on bromine. Okay. Now everybody has a full octet, right? Because bromine has these 2, and then 4, 6, 8 from the 3 bonds. The oxygens all have their octets filled as well. So it looks to me like this is going to be the structure where the octet rule is obeyed for bromine. Now I have to do formal charge calculations for each of the atoms. So looking at this oxygen here, free oxygen would have 6 electrons, but here I have 1, 2, 3, 4, 5, 6, 7, half the bond, 7 electrons associated with it. So I'm going to have a formal charge of -1 on that oxygen. And the same for the other 2 oxygens as well. For bromine, free bromine has 7 electrons. And I'm going to count 1, 2, and then half the bond, 3, 4, 5. So 7 minus 5 equals 2. So I have a 2 plus formal charge on bromine. So let me redraw my structure again with a little bit neater. I have bromine and these 3 oxygens. I have a nice lone pair on bromine. I have full octets on all of my oxygens. I know you can hear the tappity-tappity of my pen making all of those lone pairs. And then I have all these formal charges here. So this would be one resonance structure. This is the one that I get if I use the handy hints. But I'm also asking you here to draw a resonance structure that gives a formal charge of 0 on bromine. For that one, I'm not going to be able to use the handy hints, am I? Because I'm going to have to expand bromine's octet in order to do this. I can do that because bromine is all the way in the 4th row of the periodic table. And as a heavy element, it can dip into its d orbitals and it can expand its octet. So what I'm going to do to draw that structure is take one of the lone pairs on oxygen and kind of move it down to become a double bond. So if I try that, let's say I'm just going to do it with that oxygen. Let's see if that's enough to kind of quench the charge on the bromine. Oh, one thing I forgot to mention. Hang on. One thing I forgot to mention is that the formal charges should add up to the charge on the ion. So 2 plus 3 minus gives me the minus charge, and that makes sense because it's BrO3 minus, so I should have that -1 charge. Sorry, I forgot to mention that. Okay, so let's say I still have the same number of electrons to play with, right? I believe it was 26. So I just want to make sure I take those 26 electrons and arrange them in a different way such that I can reduce the formal charge on bromine to 0. So let's see if I can do that. 2, 3, 4, 5, 6. So that would reduce the charge somewhat, but it would be even better if I could do it twice. Then I can actually get a 0 formal charge on bromine. So I'm going to try doing it by making another double bond here. Can bromine go all the way out to a 2, 4, 6, 8, 10 dectet? Sure. It's deep in the periodic table, so it's just fine expanding beyond the octet. All right, so now that I've drawn this molecule, the reason I drew it this way is because I wanted to be able to subtract 7 from the 7 electrons that bromine has, the 7 valence electrons that bromine has. 1, 2, 3, 4, 5, 6, 7. So that's why I did this. I wanted to reduce that formal charge to 0. Now the only atom actually that has a formal charge here is going to be this oxygen. So if I look at this structure, the negative charge on bromate comes from the negative formal charge on the oxygen. So these are both resonance structures. They are non-equivalent. They're not the same. And we want to decide which one is better. So these are non-equivalent resonance forms. Which is better? Well, the one on the left obeys the octet rule. The one on the right minimizes the formal charges. In fact, it reduces the formal charge on bromine to 0. They both have 26 valence electrons that are arrayed properly. But I would argue that the one on the right is preferred because bromine is just fine expanding its octet. So the one that has the formal charges minimized is probably going to be the bigger contributor to the truth of the molecule. And of course, for this particular one, I could also draw, for the one on the right, I could draw 2 additional equivalent resonance forms that are just essentially rotated by 120